So the idea of these tectonic stresses and then the resulting strain is the development of mountain building or orogenesis. So when we have ocean plates and continental plates coming together, so you have the ocean plate subducting under the continental plate, you can get mountain building along that plate. The coast range is kind of that localized uplift from subduction. The Cascade Range and the Andes happen a little more inland from that direct subduction and create these larger volcanic mountain range. You get these fault blocks that we talked about from the basin and range, these tensional cracks. When you have continental plates interacting, you get high mountain building and crustal thickening. And then you can have ocean plates diverging or converging and get island building, and usually that's as a result of volcanic eruptions, which we'll talk about next. So to finish up this section, we want to talk about earthquakes in specific terms. So all of these different kinds of faults, what we experience then is that at that moment of fracture, we experience that as an earthquake, and that fracture can come from a normal fault or compression. A normal fault or tension can be caused from a reverse fault or compression or a strike-slip fault where you get that shear stress. So when we're looking at an earthquake, we're talking about that sharp release of energy that occurs at the moment of fracture, the moment that rock actually has that reaction to the strain. And that is what we call an earthquake. Now, the fault is that crack, that plane of the surface that has been broken. And so we talk about Portland being built over several faults. They may not be active, but there are areas where you would see rock layers not lining up, right? So you get those ideas of displacement. The focus is the spot where the break begins. That's the beginning point of the fracture. And then the epicenter is that point on the Earth's surface directly above the focus. So the impact from an earthquake to humans and human structures, or the landscape in general, is dependent on various components of the earthquake event. One is, how deep is the focus? If that focus is 10 feet under the surface, people are going to feel that because the movement of that seismic wave or the energy released by the rock break doesn't have to go very far, so it doesn't get dissipated or absorbed in the rest of the rock. Lots of times they'll talk about a town being 10 miles away from the epicenter. So obviously the farther you are from the focus and the farther you are from the epicenter, the less damage you're going to feel in that earthquake. It also depends on the type of rock or sediment that the event happens on. So if you are on a granitic bedrock and there's an earthquake, you may not feel that as much shaking as somebody who's maybe living farther away, but they're living on a very loose soil sediment, maybe an old gravel pit or valley sediment that's been filled, that's kind of unconsolidated. And so depending on those components, earthquakes can have huge impacts or smaller impacts. So when you have that earthquake or that sharp release of energy, there are two kinds of motions that the seismic energy is released. there's a P wave of energy and then an S wave. And the P wave is the primary wave, and it is the fastest, it's the first, and it goes in a straight radiated direction. And so if you look at this little cartoon with a slinky, if you pull that slinky back and then push it forward, that motion is going to transfer in a straight line, and when it gets to the object, you're going to feel a boom. The second wave, which comes second, is after the primary wave, is the secondary wave, and that's the most destructive because that wave has more of a side-to-side, up and down amplitude to it. So this is where a lot of the shaking, the back and forth, where things are knocked down, occurs. And of course, there are earthquake monitors that record the amount of movement in the ground surface, and they also use these monitors around volcanic regions to kind of check for small rock movement inside a volcano that could be a signal of lava being able to start moving up a throat of the volcano or being active. So we measure earthquakes in two ways. One is, we'll do this one first because it's first, is the modified Mercalli intensity scale. And this shows people what is happening on the surface. What are people feeling when they have an earthquake? And it goes from a modified Mercalli intensity of a 1 where nobody even knew it happened, to, only if you're kind of laying very still could you feel that. Sometimes when you're outdoors walking, you don't notice it, but when you're sitting still, you will, all the way to an 11 with damage. You can see the waves, the ripples on the ground from the secondary wave. Things are thrown into the air. An 11 is there's not much standing, everything's destroyed. So the modified Mercalli has more of an intensity of experience. The scale people are more familiar with is the Richter scale. And the Richter scale, and I'm realizing this is kind of an old image because we are up now to the predicted earthquake in Oregon is a 9.1, and this is an 8.9, and you might say, oh well, a 9.1, that's not big, but this is a magnitude scale with a logarithmic base of 10, so that each tenth of a scale change is a huge amount of difference in the effect. So if you can look at this, let's say a 7 was the one in California, the Loma Prieta, that took down the bridges, and an 8 is this great San Francisco fault in 1906. The Alaska, I think that was somewhere between an 8 and an 8.9. The largest recorded, and that has now gotten higher. The one in Japan was higher than this, offshore in Chile in 1960. And the interesting thing is that the earthquake in Chile is the result of seafloor subduction underneath the continental coast, and this is very similar to what we will be experiencing in Oregon, Washington, with the Juan de Fuca plate subducting under our coast. It's a very steep plate. It's subducting relatively rapidly, and so when these plates get stuck, they build up a lot of energy, and when finally some movement happens, that is the quake, and it releases the energy. So the longer that these plates are stuck and that strain is happening, it's compressing, and then finally when it breaks, that's the energy release. So the Richter scale is a magnitude scale, and I think 9.1 may be the highest recorded so at this point in time. A couple of things that happen as a result of an earthquake is liquefaction. And remember I said a few slides ago that if you're living on the valley floor or a gravel area, you might have more damage than somebody living on bedrock. And part of that can be as a result of this phenomena called liquefaction. So if you think about, and I like to think about this sometimes at the beach because it's a great example. If you're standing on the beach, you're, down by the water, but the water's not where you are, but you're close, and you have sand grains, and there's holes in the sand grain. And if you start stomping your feet fast, you can create a puddle of slurry, and that water can be pushed up between those sand grains and turn that into liquid, thus the term liquefaction. And liquefaction can cause a huge amount of damage. It can create these sand volcanoes that will boil up. So you have saturated water, you get a lot of shaking, and the water loosens up and separates the sand grains and can boil up. So here's, well, that's not a great example. Forget that example. Here we go. We're going to go down to this. This was a dry field, and all of these kind of bubbles are sand boils that bubbled up. Here are apartment buildings, a magnitude 7.4. So these were built on sand. The liquefaction that happened as a result of the earthquake just caused the land to become unstable so that these buildings just slowly toppled over. So another example. So one of the interesting things to me is here's a map of the San Francisco Bay Area. And they being the USGS, I believe, has mapped out the susceptibility for liquefaction or liquefaction. And you can see that the turquoise here is very low. So this is probably on bedrock. And so if there's an earthquake, there may be some damage from the secondary wave, but it won't be as devastating as here in this maroon area or the red area. These are very high areas of liquefaction susceptibility. And when we look at a map of that area, it's these buildings here. So we have infilled so much of, we being humans, have infilled so much of these bay areas in order to extend buildings that these are at a huge damage potential. This is one of my favorites. I don't know why I like this one, but in 65, the earthquake in Seattle, magnitude 6.5. You can tell they definitely lost some ground here. So earthquakes can cause landslides, they can cause liquefaction, and they can cause tsunamis. And a tsunami is created by water displacement. So if you were to have a wash tub in your backyard and you drop a brick in it, not just gently lay the brick, but you drop a huge brick in it, that brick is going to displace water, and that water has to move somewhere out of the way. And that's basically what can cause a tsunami. So there can be huge shaking, or there can be a large piece of material that falls into the water that creates that water displacement. The tsunami in Indonesia in 2005 was a result of an underwater landslide where a huge underwater mountain basically fell and displaced water and moved it up into the shallows in Indonesia. So if you have, say, an earthquake along the floor, the ocean floor, that land, so remember we talked about vertical displacement, either land drops or land moves up, but that displacement can cause a drop in the sea level. So water will come in to fill that depression, and will often overcompensate and then start this oscillation of water moving forward. Okay, so they can be hugely destructive. This is an example of an earthquake in Peru that caused a tsunami in Japan. And this is the result of the tsunami. And if you think about how far that wave of water had to transfer, it's pretty phenomenal about the amount of power and damage in that water. This is from the Alaska quake. Boards were moved, and the tsunami, moved lumber into buildings and through tires. Just kind of phenomenal. Along the Oregon coast, we have a lot of, you'll notice these tsunami information warning signs in case of earthquake, go to higher ground. We just, every fall, there is a great Oregon shakeout where we kind of think about tsunami potential in Oregon. And if I can go back to my coastal plate here. So we have the potential for a 9.1 or higher subduction zone earthquake along the Oregon coast. And based on research in other areas with similar geology and geography and topography, the expectation is that this could be fairly devastating, where we could have tsunamis along our coast, some of them moving, inland and shallow areas. And the thing to know is that in Oregon, because the plate boundary is so close to the coastline, that if we have an earthquake, the expected arrival of the wave would be 20 minutes. And that's not a lot of time for people to turn on the radio and see if there's a tsunami coming. And so the best advice right now is when you're on the coast, you keep your shoes under your bed, and you be ready to go if you need to. And if you feel an earthquake, you need to go to higher ground immediately. You don't have time to wait and see if there's a tsunami. We are getting more tsunami warning systems, but by the time you have 5 minutes of shaking and pick yourself up off the ground and figure out, where your jacket is and your shoes, there's not a lot of time to get to higher ground. So it's really important that, especially in an tectonically active area like Oregon, that we take those warnings very seriously.